Welcome to another video. Our last video covered the basics of generalized method of moments, or GMM estimation. And in this video, we're going to introduce some simulation-based methods that can be used to estimate our structural model when we have really hairy or involved computational steps. And typically, this would be numerical integrals of some sort. And we'll compare and contrast three different methods that are simulation-based. First is simulated maximum likelihood, or SML. Second is simulated method of moments, or SMM. And third is method of simulated scores, or MSS. Each method has different trade-offs between computational tractability, statistical efficiency, and practical implementation. So it's important to understand the trade-off that you face when choosing one of these methods to estimate your model. And before we get too far into this, let's just remind ourselves how simulation is helpful when we have integrals in our structural model. And the first question might be, why do we have integrals in our structural model in the first place? Well, typically this will come from two different sources. The source we talked about in an earlier video was preference heterogeneity. Typically, we need to take some integral over some distribution of unobservables in order to take an expectation. And that could be over the distribution of unobservable preferences that might differ across different decision makers in our population that we're analyzing. And then a second one, which is under this same umbrella, is integrals about future expectations. An example of this is in one of my dissertation papers where decision makers needed to take expectations over labor market shocks in all the different locations in the United States. And this involved predicting what the future shocks would be when making their decision about where to live. So that's an example of where a dynamic model would lead to this sort of numerical integration as well, not just for preference heterogeneity. And if you look at the corresponding GitHub repository that goes with this set of videos, problem set 4 in that repository covers some exercises for how to implement in Julia the numerical integration that we cover. We contrasted quadrature for low-dimensional integrals versus simulation-based or Monte Carlo integration for higher dimensional integrals. So that's a review of why do we need to use simulation in the first place. Typically, it's to solve some integral that is arising in our model that we can't just use a closed form solution to compute. If you go to the Kenneth Train textbook on discrete choice modeling, he covers three simulation-based estimators. The first is simulated maximum likelihood. Some people might call this maximum simulated likelihood. So you might see it as either SML or MSL or SMLE. The second is simulated method of moments, which again, sometimes people will say method of simulated moments instead of simulated method of moments. So you might see it written as MSM or SMM. Then finally is the method of simulated scores, which is universally depicted as MSS when abbreviated. And in that problem set 4 of the accompanying GitHub repository, we went through simulated maximum likelihood when we did the Monte Carlo integration example. In this video series, we'll be focusing mainly on simulated method of moments, so we'll revisit that in a little bit. How does simulated maximum likelihood work more generally than just the example that we went over for mixed logit? Well, basically the idea is that we want to replace exact probabilities with simulated approximations. Let's remind ourselves what the likelihood function looks like for a mixed logit model. We have the sum over the individual decision makers of the log of the individual likelihoods, and those individual likelihoods are a messy function of the parameters that we're trying to estimate, as well as the data, the covariates and the choices made. And in this example, our choice probabilities are a function of some unobserved variable, z, that we need to integrate out of the individual likelihood. So everything that's in this individual likelihood, we can just denote pi of theta. And the idea is that we need some way to compute this integral because we can't just take the log of the integral. That's not the same as the integral of the logs. Same with this product over the j's. The integral of the product is not the product of the integral, generally speaking. And so we take this integral and we replace it with an average over draws of z from some distribution. So here the superscript r is indexing the rth draw from the distribution of f. So we can call everything that's in the log of this second equation p check I of theta, and p check I is computed by averaging across many draws of the z's where we're drawing from the distribution that z is defined by. Now the key issue with simulated maximum likelihood is that there's bias arising from the log, because we can't take the average of the log is not the same as the log of the average. This is also known as Jensen's inequality if you've taken a prior economics course. So even if p check I was an unbiased estimate of pi, log of p check I is going to be biased for log of pi. And so this simulation bias is going to affect the properties of this simulated maximum likelihood estimator. And in particular, we're going to have to pay attention to how the number of individuals in our sample grows as the number of draws that we take from the distribution of z grows. So we can think of three cases. So one case is we just keep r fixed, and as we grow the sample size of the decision makers, what's going to happen to our estimator? Well, it's going to be inconsistent. It's not going to give us the answer that we need it to as we let the sample size grow to infinity. We can also let r rise at the same rate as the sample. As long as r is rising alongside n, we're going to get consistent estimates. And then if we let the number of draws grow faster than the square root of n, then this log bias is going to disappear. We're going to get something that is asymptotically efficient. So the practical implication is that if we have a larger sample of data, we're going to need to use a larger number of draws. So now let's talk about simulated method of moments. And in simulated method of moments, we avoid this bias from the log. And how is that possible? Well, because in a prior video where we talked about the binary logit, we're just trying to match d with p. There's no log of p happening. That's the main reason why we don't have this bias in simulated method of moments. What we're trying to do is match moments of data with moments from a simulated model. And so we want to find the theta that equates those two or gets them as close to zero as possible if we're taking the difference between them. And basically this g function, we're going to modify so that it compares the actual moments in the data with the same moments from the model. We don't have to do any log transformation because of what I said. We're just comparing d and p. We're not comparing d and log p. So we're not going to have a simulation bias in this case. So how does this SMM work? Well, basically we have our classical moment condition is we just take m from the data and we match it to m of theta from the model. So this is like y, and this would be x beta in the OLS model. And then in simulated method of moments, we're going to replace m with m check, which is simulated. So m check is itself going to be an average over many draws from some unobservable variable that's going to influence this moment condition from the model. Obviously, if it's OLS, we don't need to worry about check. We can just use x beta. But in more complicated models, we're going to have to deal with these integrals over latent variables, and this is a way to do that, where we just take every possible value that variable could take on and average over it, weighting by the density of the distribution that of values that it could take on. And we're going to have the same exact objective function. This j of theta is going to be exactly the same as it was for generalized method of moments. And we have a weighting matrix, which we would again want to use as the inverse variance of the g. So now let's take a step back and think about how GMM, not SMM, but GMM would work in a multinomial logit model. We did the binary logit case in a prior video, and now we want to do the multinomial logit. So here we have I and j subscripts because we have more than two alternatives to choose from. So what we're going to do is we're going to get a system of n by j equations of these residuals, and we're going to weight them by the n by j times n by j identity matrix. And then this is going to give us basically nonlinear least squares for the multinomial logit. So now let's think about how to do this for simulated method of moments. We're going to want to compare dij with p-check ij of theta. And then we're going to have this same n times j number of moment conditions, where this p-check ij is some kind of average over all the possible values that pij could take on, given what we are trying to integrate over with regards to the latent variables distribution. The key advantage for SMM over simulated maximum likelihood is that these probabilities are entering linearly. You can see there's no log in this equation at all. And so that's going to reduce the bias from Jensen's inequality that arises in simulated maximum likelihood. So as long as we can get an unbiased p-check estimator, then our estimates are not going to be biased. And even if we let R be fixed, we're still going to get consistent estimates. Now, maximum likelihood is always going to give us the most efficient estimates, so we are going to sacrifice some efficiency when we use simulated method of moments, but it's not as severe as the simulated maximum likelihood. Then finally, what is method of simulated scores? Well, basically, it's a way that we can use the score function in our model to inform us about the estimates. So what is the score function? Well, it's the derivative of the likelihood with respect to the parameters. You might call it the gradient vector. And we want to find the theta such that the score is 0. We want to minimize that score to estimate the parameters. And so the idea with method of simulated scores is that we can use other ways of generating the score than just the partial derivative of the log likelihood. And if we can get an unbiased score simulator, then we can have consistency of our estimates even for a fixed R. But the question is, can we get an unbiased score simulator? And the answer to that is that it's very difficult to do. So MSS is going to be efficient when R rises at any rate with n. So that's better than MSL. But the limitation is that it's not so easy to find an unbiased score simulator. And so for all of the reasons above, you don't see this used very often in empirical research. And I'm not going to cover it any more than just to tell you about it and the reason why it's not used very frequently. So that is a little bit of background on these simulation-based estimators. In the next video, we'll go deeper into simulated method of moments, and then later on, we'll do a coding demonstration to show how you can actually use this in Julia to estimate the parameters of a model. I hope you've liked what you've seen so far, and you'll join me in the next one.